Hi, I'm Avery, and I'm going to be presenting my project, which involved analyzing a series of images of a star system over time in order to construct a light curve and investigate an exoplanet candidate, TOI 172AB. So, the general idea behind this project is based on how exoplanets are detected in modern astronomy. Since most exoplanets are far too faint and distant to observe directly, we detect them indirectly through their effects on their host star. So, one of the most common methods is the transit method. In this method, if a planet's orbit is correctly aligned, it will periodically pass in front of its star from our point of view. And when that happens, the planet blocks a small fraction of the star's light, which causes a temporary dip in brightness. Even though this dip is usually very small, it can still be measured with precise observations over time. So, for this project, I was given several images of the same star system taken at different times. And each image shows the same star field, but individually, they clearly don't immediately reveal any planetary information. So, the first step was turning these images into usable numerical data. And to do that, I used a method called stellar photometry, which is the process of measuring the brightness of a star in each image. So instead of just relying on visual inspection, I input the coordinates of the target star in the first image, and then I extracted the numerical brightness values for the host star across all the images using an exotic program. And to help improve the accuracy, I compared the target star to some nearby reference stars in the same images. These reference stars are typically assumed to have constant brightness, so they help correct for things like atmospheric conditions, exposure differences, or instrument noise. After the code repeated this process for all the images, I ended up with a consistent data set which shows the brightness of the star over time. Next, the code plotted the brightness values over time and created this, which is called a light curve. So, a light curve is one of the most important tools in observational astronomy because it allows us to see how an object's brightness changes over time. In an ideal case with no planet, the light curve will be mostly flat, but in real life, there's a lot of measurement noise, and also the star's luminosity will fluctuate, so there's going to be some small random variations. However, if a planet is transiting the star, we expect to see a more distinct dip in brightness. And when I plotted my data, I observed this dip, which is consistent with its transit pattern. So, another really important thing in exoplanet detection is not just seeing that the dip exists, but also making sure that the signal is statistically significant enough. In astronomy, this is often measured using something called sigma, or standard deviation. Sigma is basically a measure of how much a data point deviates from the expected average noise. So, a 3 sigma detection means the signal is strong enough that it's very unlikely to be caused by random fluctuations. And in exoplanet science, a 3 sigma or higher signal is usually considered a minimum threshold for reliable detection. 3 sigma would mean that the light curve size is approximately 3 times greater than the size of the average unrelated deviation. So, the way to find out how reliable the detection is to find the transit depth divided by the transit depth uncertainty. Both of these are here in this image, and the transit depth can be found by dividing the area of the planet, which is approximated as a circular disk, by the area of the star, which can also be approximated as a circular disk. This plus or minus number is the uncertainty, and the detection I got was 6.69 divided by 0.92 sigma, or approximately 7.27 sigma. So it's very unlikely to be just noise. Beyond just confirming the transit, the faded light curve can also give us a lot of really important physical information about the system. For example, the depth of the dip is directly related to the size of the planet compared to the star. A larger planet will block more light, which creates a deeper dip in brightness. So, by measuring how deep this dip is, we can estimate the approximate radius of the planet relative to its host star. The shape and duration of the dip can also provide information about the planet's orbital speed and how long it takes to cross the star's disk. So, after completing the analysis, I submitted my results to the platforms AAVSO and also NASA's Exoplanet Watch. These platforms regularly collect observations from both professional and citizen scientists and use them to refine and improve data on exoplanets. So, thank you so much and happy graduation!